reminding me. I'm very absent-minded. Okay, but fortunately only like 2 minutes we left. Okay, okay, yeah, thank you. Thank you for reminding me. Very absent-minded. Really, too bad. So let me remind you what the field is, vector field is. So this x, y, and z, these three components, are coordinates of some point in 3D space. And there are lots of points in 3D space, actually infinite number of points. And so if every point in this 3D space get associated vector f, associated with this point, with this location, it means that we are dealing with the collection, with huge collection of vectors designed over these points. This collection is called vector field. So just very easy. I mean, it was just a reminder. But you know what? Today we are going to deal with 2D fields, vector fields as well. In case of 2D, of course, you can imagine like how it's going to be like, look like. So vector f this time has two coordinates, as well as these components. They have two components as well, because all is happening on plane, which is 2D space, only two components. So we are going to consider both cases today. Okay, so this is what is given to us today, vector field, either 3D or either 2D. What next? We need to find out now what is the curl is. You know, I decided to split this first chapter into two paragraphs. So let's call the first paragraph 1a, which will be about calculation of curl of vector f, of vector field f, calculation, just calculation, definition, and so on. Note how I put two arrows here, because the first arrow is above vector f, because it's vector, and the curl itself gets a bigger arrow because this is a vector. Okay, so what is the definition of curl? The definition, you know, looks very easy actually, very formal definition. So the curl vector, let me use black instead. So curl of vector field f, which is vector itself, is just cross product of our favorite vector nabla, symbolic vector nabla, times our vector field. That's it. Very dry definition, very mathematical one. And in this first paragraph, we don't need to know what physical concept or geometric concept is hiding behind this formula. The purpose of this first paragraph 1a is just to learn how to calculate it, which is quite easy, to be honest. Let's expand this expression, because we know that nabla is a symbolic vector. Let me remind you, by the way. I don't know, I don't have space. Nabla is symbolic vector, d over dx, the first component, the second d over dz, and the third d over dz. Oh, sorry, I said something wrong. So what is weird about this nabla vector, that it doesn't have any functions here. Usually you have some function. And this is the purpose of this nabla operator, because these are actually placeholders. Once you start perform some operation over this nabla vector, these blank spaces immediately get filled up. This is the objective, the purpose of inventing this nabla operator. Okay, so let's get back to our task at hand. So we have cross product here. Of course, you should remember cross product. The first, this is the determinant. The first row is always vectors I, j, k. The second row will be coordinates of our nabla, d over dx, which are symbols again, but it doesn't matter because everything works just fine. And as for the last row in this determinator, these are components of vector f, which we denoted as p, q, r. So that's it. So this is curl. Some people even prefer to remember, to memorize the formula for curl in this form rather than this one. Of course, this is more concise, of course, but somehow it's easier to remember this one. Okay, as you may guess, the next step will be just to calculate, to do some concrete example. So I'm removing this page now. Okay, so I chose question 2b from our tutorial sheet. So it's going to be question 2b from our tutorial sheet. And it goes like this. You are given a vector field f, which has three components, like 3x squared minus y squared. The second component is x squared minus 2xy. And the last component is 3z. So these three components are our p, TQR. TQR. And they ask us, actually, in this problem, in this question too, they ask you to calculate cross product of nabla cross F. But you know already that this is curl, so they actually ask you to calculate the curl. Okay, let's do it at least once today's tutorial. So the first row is IJK. I'm trying to save more space for these expressions. Okay, for the third row. Okay, the second row is the same all the time. This is our nabla operator, d over dz. And the last row should be filled up with PQR. So this time we have complete expressions. 3x squared minus y squared. This is our P. Q is x squared minus 2xy. And the last component is 3z. Okay. And now to calculate our curl, we need to pretend to be calculating determinant. And the best way is to expand it along the first row, of course, as usual. So let's start with I. I times what? I prefer to use brackets. There's nothing mysterious behind them. It's just brackets. Okay, so we need to cross out the first column and the first row. Okay, and we will be left with this determinant again, 2 by 2 determinant. But I'm sort of lazy to write down every single detail. I think that it will be pretty easy for you to do it, a little bit faster. So this guy times this guy minus this guy times this guy. Of course, you know this rule. But it's not pure multiplication. When you say that this guy times this guy, it's not actually real multiplication. It's just that this 3z fills up this space here, this blank space here. So we will have d of 3z by dy minus this times this will give us d of x squared minus 2xy not divided by dz. You shouldn't say divided, by the way. Okay, let's move further on along this row. The next term is for element minus j. Again, I'm going to cross out this the second column now and the first row. So it will be this times this will give us d of 3z over dx minus this times this minus d over dz of this expression 3x squared minus y squared. And finally plus k, the last element in the first row. So I need to cross out the third column and the first row as usual. So this times this will give us d over dx of this expression x squared minus 2xy and minus this times this minus d over dy of 3x squared minus y squared, parentheses are closing and brackets are closing. And so now it's time to calculate these partial derivatives, actually. Partial derivatives. So I'm checking that you still can see the first row. Okay, I times what? You know that when you want to do partial derivative relative to y this time with respect to I, all the other variables gets frozen. So in our case, this guy is frozen. It means that this is a constant. And any derivative of the constant is always 0. So 0 minus, the same story for this term. We are very lucky. This is 0 as well, because there are no z's here inside. Okay, very nice. I really like this. I don't mind this situation. Okay, let's move to the second term, minus j. Again, the same story. Look at this. We need the derivative with respect to x, but no x's here. It means that this is constant and derivative is 0 again. The same story here. So far, we've been very lucky. Okay, the last term has left to us. The last term. This time we are not so lucky. It's time to, to use our brains at last. Okay, so the derivative should be taken with respect to x, and it means that y serves as a constant here. So be careful with the second term. Okay, as for the first term, the derivative is very easy, 2x. And in this case, you have x here with coefficient 2y. So it means that 2y remains here. Okay, and the last term inside these brackets. So we need to imagine that our x is frozen now, and that is why the whole first term here in this parenthesis is constant, and that is why it's 0. I will write it like this. And only this term will give us a derivative which is minus 2y. So that's it. And now it's time to simplify a little bit. So we can rewrite it as the first component with 0 coefficient, 0 times I. The same here, plus, we can even put plus, minus 0, plus 0, it doesn't matter. And here we need to find some, I can see that y's get cancelled out here. So we are left only with 2x as the third component. And you know, it's even better to rewrite it without this annoying guys, I, j, k. We can rewrite it as a row vector. So 0 the first component, 0 the second, and 2x the third. So this is it. This is our answer. So this is our curl for this vector field. That's it. So that's how you should calculate it. And I would recommend you to go over the whole question too, actually, just to get experience. Maybe you may find this task very annoying, but just check yourself, check your knowledge. And besides, during test 2, as you realized from the previous test, you will have the time pressure. And that is why it would be a good idea to get really good practice to be able to solve all these, unknown things quite fast. It will save you time for something more serious, something more deep. Okay, so now we know how to calculate. Let me even record this fact. So homework for you will be to go over question 2. I would strongly recommend you just to get this experience in calculation of curl. Okay, so we finished with part or with paragraph 1a. Now it's time to move to paragraph 1b, subchapter of this first part, which will be curl again, curl of vector field, but this time we are going to deal with visualization. Very interesting topic, much more exciting than the previous one. The previous one was just about how to use the formula. That's it, quite boring. But this is quite different. Maybe if you went through this tutorial sheet before this session, you noticed this question 6. Do you remember this? Question 6. You are given a vector field and you are asked to determine the sign of curl. In different places of this vector field. How to approach this task? It looks really daunting, but in reality, it's much easier. If you watched the recording of your last tutorial 6 from the last time, you probably noticed that I explained to you how to deal with these diagrams in a case of divergence. These were like the last 15 minutes of that video. So I have to admit the divergence was much more difficult. You needed to perform the test, and the test wasn't very easy at all. But as for curl, just relax. It's much easier. It's much easier. And nevertheless, I decided not to do this question 6 because it's better to leave it for you for the homework. It's better to just to get you prepared. So what I'm going to do now, I'm going to give you quite a few small examples, just to develop this understanding. Okay, so the first example will be very easy, the simplest vector field ever. So these vectors, they are all parallel to each other, and they all have the same length. There's nothing easier than this. So very easy, very simplistic vector field. You can imagine this being a canal, not even a river, because rivers are always more sophisticated, more complex. Just a canal with a very regular water flowing from left to the right. And all the particles, all the water particles in this canal, they have the same direction of movement and the same speed. The length of the vector reflected speed. Okay, and our task is to determine the sign of curl. If it's negative, whether it's positive, or maybe it's even equal to 0. Okay, so the curl, if you remember lectures, the curl shows if there is any rotation present in your vector field. And at first glance, if you look at this picture, you will say, no rotation here as well. But of course, for this particular vector field, maybe things are easy. You can see things with a naked eye. But in some cases, it can be really, really tough, because some curls, some rotations are just hidden from the human eye, So okay, let's start. So in other words, we need technique, we need algorithm, very reliable technique, some test, just like in the case of divergence. So what sort of test is this? First, I want to tell you that actually curl consists of two components, two terms. The first one is general rotation, general rotation, general rotation, and the second term is local rotation. You know, the good equivalent is the example, very famous example from physics, from mechanics. So when they were explaining to you the concept of general maybe speed, velocity, and local velocity, maybe these were different words, actually, different terms, but it doesn't matter. The idea is the same. So maybe you remember this example of the train, moving train, and you are sitting inside the train. And all of a sudden, you stand up and go to the toilet inside the train, of course. So what happens here? What is the situation? Remember, imagine that you are observer who watches this train from outside. You are somewhere on the station or somewhere in the fields, and you're watching this train passing by. And also imagine that this train is transparent, so that you can see the person who walks inside the coach from his seat to the toilet. So what about velocities of these people? The train moves. That is why this is the general velocity, general motion. And as for the person moving inside the coach, it's a local movement, local velocity. And the summary velocity will be the sum of these two components, these which are vectors, of course. So the same thing happens here, actually. So curl is the sum of these two components, general rotation and local rotation. So we need to determine each term one by one. So how can it be done? We need some reliable test, and this is the most exciting, the funniest part. That what tests we usually perform for general. Let's rewrite it like this. So curl is J plus L. So general rotation plus local rotation, just for brevity. So to determine general rotation, you need to use point. You should imagine that you have a very small point, just infinitely small point, and you need to place it in any in arbitrary location of this vector field, and see what happens. And for determining local rotation, you need to use stick, the matchstick, or just stick. So how exactly we need to use them? Let's get back to our field. So let's start with general rotation. Okay, so we need to use point. Let's imagine that you put point somewhere here, in an arbitrary place. What happens to the point? Of course, you can immediately realize that the point will start moving with the flow in this direction with this length. And it doesn't depend on the location. Our vector field is so easy, so straightforward that it doesn't. The behavior of this point doesn't depend on the location. But what about rotation? Does this point rotate? No, of course not. It goes by straight line. That is why general rotation is equal to 0. You might feel a little bit puzzled because it was clear from the very beginning. Yes, general rotation can be detected by naked eye, actually, because you can see the behavior of these arrows, and it's very obvious that they are not rotating. But things are much more complicated, much more sophisticated, I would say, when it comes to local rotation. You can't detect a local rotation by a human eye, by naked eye. You need this stick as a test. So this is quite a funny part. So how to, where exactly we need to put the stick? The stick should be put orthogonal to these vector lines, something like this. So if we put a stick, the second thing, we need to nail down this stick to the bottom of our canal, in the middle, so that the stick couldn't move with the flow, couldn't be carried with the flow. The stick should be at the same place all the time. And then it might start rotating, by the way, because this vector field influences it, this flow. To determine this rotation, whether it happens or not at all, we need to look at the two end points of this stick. So let's look at the top end of the stick. What happens? You can immediately see that there are arrows here. It means that this the flow of water tries to carry this end in this direction, of course. But you know, the same happens with the bottom end of the stick. The same water, the same flow tries to move it this way. What will happen to the stick? Nothing. It can't rotate because you know, these two forces are balanced. So there's no local rotation at all here. But sometimes this stick might start rotating around its axis, around this nail point. Okay, so but our first example was the easiest one. So our conclusion is this curl is this guy plus this guy, that they are both zeros, so our curl is 0 as well. So you were right from the very beginning. Curl is equal to 0. But wait a bit until we move to the next small example. Okay, so the next example will be the same canal, but the flow is a little bit more sophisticated. So vectors are parallel to each other, just like in the first example, but they have a tendency to become shorter if you move downwards. So these are shorter, and these are even shorter, and so on, so on, so on. So you now see the tendency now. This is a very strange canal. I don't know what's going on, what's wrong is this canal, but it doesn't matter. We are not worried about things like this. This is just our vector field for us. Okay, let's perform tests for general and location movement. What about general? For general movement, we need to place a point somewhere and see how it starts moving. Yeah, it starts moving just like in the previous example, by straight line, no rotation at all. So no general rotation. And again, general rotation could be easily seen by naked eye. You actually do perform this test with a point when you see these vector lines, but maybe unconsciously. Okay, but as for local rotation, it's usually much more interesting. Okay, let's put our stick again. So the stick has two, stick is orthogonal to our vector lines. And the second requirement, we nail it down to the bottom of our canal. And now we need to see at the points of this stick. And now I suspect that things will be different. Look at this. This point has this, speed, velocity, and this point has a tendency to move in the same direction, but much slower. What will happen to this stick? Okay, that's right. It will start rotating around this nail, and so rotation happens clockwise, by the way. So the sign of our local rotation is negative. You know why? Because in mathematics, the positive direction is considered to be anti-clockwise, counterclockwise. And in our case, it's clockwise. This is why it's negative. Okay, and as for curl, 0 plus negative will give us negative. So the curl is negative in this case for this field. So you see how difficult it is to determine local rotation without this stick, without this testing stick. Absolutely impossible. You can only see general rotation immediately. But as for local, you need to perform this test. And of course, you realize that I performed only one test with the stick. But of course, you realize because everything is so homogeneous here, so uniform, that is why the result will be the same. Irrespective of the location of the stick and of the point. Okay, now it's time to make our vector field a little bit even more sophisticated. What if these vectors are not going in straight line, are not parallel to each other? What if they are forming circles? It will be much more interesting. But as I'm not a very good artist, I just prepare this circle first, and after that I'm going to draw vectors, to sketch vectors after that. Otherwise, everything will be very messy. So this is just a preparation. So my vector field looks like this. So there are vectors here going along this circle. They have the same length, all of them. Then these vectors are the same. These vectors all have the same length again. Let's start with the example when all the vectors in all the vector field have the same length, but this time the direction is more interesting than the previous case, and so on and so on. So you get the idea. Okay, so let's start with general rotation again. General rotation, if you put a point in an arbitrary place, of course, this point will start rotating around this center. And rotation will be clockwise, that is why it's negative. Okay, and again, To determine the local rotation, we need a stick. We need our favorite stick. So let's put it somewhere for me here. So sticks should be perpendicular, orthogonal to vector lines, and it should be nailed down to the bottom of our not canal. This time it looks like sink or maybe like sauce. I don't know. It should be nailed down so that it couldn't be carried away by the flow. The only thing which it can do, this stick, it can rotate around its this nailed place. Okay, so let's see at at the end points of our stick. So this end has a tendency to move this way, and this point has the same tendency. That is why, as you know from previous examples, it doesn't rotate at all. So the local rotation is 0, and that is why the resulting curl is negative plus 0 will be negative again. Okay, but it's very difficult to see this, of course, without test. Okay, I have 2 more examples. So the fifth example will be circular vector field again. Okay, let's prepare the circles first. Okay, maybe even 2 circles would be enough, but it's too late now. Okay, so what happens now? This vector field will be pretty similar to the previous one, but the vectors are not of the same length now. So the directions of the vectors are the same. They are all going clockwise, but they have a tendency to become bigger and bigger once you move further from the center at this point. Okay, they're bigger, and these guys are even bigger. So now you see how this vector field behaves. Okay, as usual, let's start with general rotation. There's nothing easier than this. Just like in the previous case, if you place a point somewhere, it will start rotating around this center on the 2D plane. It means that rotation is clockwise, which is negative. Okay, local rotation, we need our favorite stick. Let's place it somewhere perpendicular. Nail down in the middle and see what happens. And now we have a difference because this point has very small arrow, and this point has much bigger arrow. And of course, this point will win, and our stick will start rotating in this direction. So the local rotation happens in clockwise as well. That is why both our rotations are negative, and the curl is negative as well, because negative plus negative is always negative. No problem. So as you can see, it's even a lot of fun to determine the sign of the curl. But wait a little, things are not as rosy as I'm describing it to you, because in some cases you can't give a definite answer, unfortunately, and it's quite normal. The solution doesn't always exist. You are quite familiar with this situation in mathematics. So let's consider the last sketch, which is about a circular field again, but vectors have the opposite tendencies. They are bigger here, and they're becoming smaller and smaller once you move further away from the center of rotation. So these were bigger arrows. Here they become smaller and smaller and smaller. I just don't want to sketch too many vectors not to make my drawing too messy. I think it's enough. You understand the idea now. Okay, so as for general rotation, nothing new. Again, it happens in a negative direction. But as for local one, let's have a look at it closer. So let's place our stick somewhere here, nail down it in the middle and see. So you definitely see that this side, this endpoint, has a longer vector velocity than this one, and rotation will happen this direction. It means that counterclockwise, and counterclockwise means what? Positive. And now here we have problem, because if you add up 2 terms, one of them is negative and other is positive, the result could be anything. The result could be positive, it could be negative, and it could be even 0 sometimes if these 2 terms have the same absolute value. So in this case, you can't give a definitive answer. You need to put a question mark. You just need additional information about the magnitudes of these vectors G and L. And that is why it's quite normal to get this answer. Sorry, I don't know. So okay, so I hope that you found this problem quite fun. It's very interesting to perform this test. And when it comes to question 6 from our tutorial, as I said before, it's not my intention to to go over this task. You should do it yourself. The only thing which you can immediately detect here, this vector field looks much more sophisticated than my examples, and it means that if you want to, so maybe in some of the areas the curl will be negative, in others it will be positive, somewhere maybe even 0 or maybe question mark, I don't know, I'm not sure. So you need to perform several tests with points and several tests with sticks, to determine these areas. So that's how normal questions look like. They are not as easy as the ones I just explained to you. It was just preparation, just introduction. So to wind up with this paragraph, I would recommend you homework to do question 6, and also not only question 6, it's too little, to do only one question. You have your study guide, page 88, study guide. You have there quite few examples. It will be very good preparation for your text too. So I would highly recommend you to go over these examples. And these examples, they have answers, of course. And of course, there is even example study guide where they explained it to you once again how to deal with this task. So now I think you're quite well prepared. At least you understand the idea behind it. Okay, so now it's time to move to the second part of our tutorial. Second part, second chapter will be called irrotational vector fields. Irrotational vector fields. Rotational vector fields. You know what? Irrotation, I prefer to call them irrotation as well as your lecturer, but they have other names as well. They could be called potential. It's the same, potential, and there is even one more term, solenoidal. Solenoidal. I'm not sure of the spelling, by the way. Okay, so these are all synonyms, but I prefer the word rotational. Okay, so we need definition. What are these mysterious guys? Irrotational vector fields. Very easy again. Definition is very easy. So F, vector field F, is called irrotational if its curl is 0. Curl is 0 vector. That's it. Very easy explanation. So the vector of curl reflects the ability of the vector field to rotate sticks or points, as you know from previous examples. So if the curl is 0, it means that no rotation happens. Or maybe they just cancel out each other, like it might have happened in our last example. If this general rotation is negative, local is positive, and if they have the same magnitude, it means that nothing will rotate as a result. It could be like this. Okay, but it doesn't. It shouldn't bother us. And now you realize that if you are given a task to determine, so for example, they give you a vector field F by some formula, and they ask you, can you please determine if this vector field is irrotational or not? What should you do? You should apply this definition. That's it. You should calculate the curl and see if it's a 0 vector or not. It sounds so easy that I feel sort of lazy to go through the example, to be honest, 3D example at least, because it will all boil down to just calculating curl again, which already did just 15 minutes ago. It will be very boring and not very useful for you. But the only thing which I want to point out to you is 2D case. 2D case could be done much easily, much more in a much more easy way. Let's take a note, very important note concerning this topic. Note for 2D case. For 2D case. 2D case. So when your vector field is two-dimensional, so if our vector field has only 2 components, in this case you have 2 options as to how to solve this topic. Let's write it, 2 options. It's always nice to have 2 options actually. So the first option is, I forgot to take this note in the previous paragraph. Okay, so it's all for the better. So the first option is just to rotate, calculate curl, just calculate curl and see if it's 0 or not. But how to calculate curl in 2D case, by the way? Because we have this nice formula to remember it from the first page. So the formula for the curl was this one. It assumes that you have three components, P, Q, R here, and X, Y, Z. But in 2D case, we don't have this. The third component is missing. What should we do about it? We need to know the trick. The trick is a very easy one. Look at this. So your vector field has only three components. Just add the third one, being equal to 0. That's it. And you immediately get the third component. So this is a trick. Very important, very nice trick. And after that, you can substitute this to your formula. So y, j, k, as usual, and so on and so on. I'm lazy to write it down. So you should definitely need to know this trick. Okay, what about the second option for 2D case? The second option, if you perform this algorithm several times in a row, you will start seeing patterns, and you will see that there are always two components of this curl vector, which are always 0, just always 0. And that is why it looks so annoying that you need to calculate the hot determinant if you already know the result beforehand. You can already predict that, oh, these two components will be 0 again. And that is why maybe it makes sense to remember the separate rule for 2D case. So rule just looks like this. You need to check this equality, this equation, that dq over dx is equal to dp over dy. It sounds much easier, to be honest. It sounds much easier than to calculate the whole 3 by 3 determinant. And so how to use? If this equality is true, if the equality is whole, so if yes, your field f is irrotational, And if no, of course, it's not irrotational. Oh, sorry, I'm joking my camera. So let's try out this example, especially like this idea. Unfortunately, we don't have time to apply both methods. Oh my gosh, sorry, I'm joking once again. Of course, but I think that there's nothing interesting about the first approach. You should only know this trick, and that's it. And after that, there will be no problem for you to calculate. You can do it as a homework, by the way. But now I'm determined to go over this, 2D example using the second approach because it looks so appealing, so nice. So let's do it. So I think it should be question 1J. Question 1J looks very nice in this respect. So in this question, we are given 2D vector field. F is equal to y squared minus y and 3xy squared minus x. So we have these two components, P and Q, of course, as you can see, and they ask us to determine if this vector field is irrotational or not. So it means that they want us to check the curl, but we know the trick. We have our beautiful second method, and that is why let's try and use it because it looks so nice, so easy. Okay, let me rewrite this equality here because I'm afraid that it will be sliding out of the field of view. So we need to check this equality. P over dy. I put the question mark because I don't know yet if it's true or not. It means that we need to calculate only two partial derivatives, and that's it. So let's start with the left-hand side, dq over dx. So we need to look at this expression and imagine that y is frozen. In this case, 3y squared will become coefficient, which is the derivative of the first term. And the second term will give us derivative minus 1. So we are finished with the left-hand side. On the right-hand side, we have dp over dy. Very easy. It will be 2y minus 1. As you can see, these two guys are not equal to each other. So it means that our field is not irrotational. Sounds really strange. So the field f is not irrotational. Just, I don't know if there is such term, rotational. So it's not irrotational. That's it. As you can see, it's much easier to use this short formula, shortcut. Very nice. Okay, so, and as a homework, so that's it about the second part, which was about irrotational fields. Very easy, as you can see. You only need to know a definition or this nice trick for 2D case. And as for homework, I would recommend you, I think it's question 3, even 2 questions. It's even question 1, question 3. Question 1 and question 3, I suppose, if I'm not mistaken. Does not irritation? I don't know. I'm not sure. Maybe. Sorry, I don't know. But rotation, probably rotation. Yeah, that is why I myself find this strange, this phrase very strange. Not irrotational. Okay, I'll look it up later somehow. It never occurred to me to think about it. Of course, it does make sense. It sounds very natural to call it rotational. Okay, so I think it's question 3. It's definitely about a rotational thing. No. Question 1, sorry, is not about this. The assignment is different there. So it looks like it's only 1 question, maybe. But it's not a problem because the task is very easy. Okay, so we are finished with the second part, and now it's time to move to the third part of our tutorial. By the way, it's only 20 minutes left, and this only half of the tutorial is covered. But as usual, just like last time, I'm determined to record the whole tutorial to cover all the topics. So feel free to leave, at 10 o'clock, because you definitely have next session, next lesson or lecture or a tutorial. It doesn't matter. I'm going to continue recording this tutorial so that you could watch the rest of the material later. So feel free. But maybe you have some questions now at the moment. So far, no questions. Yeah, so far it was very easy. And the third part won't be so easy. It will be very technical, the third part. And so the name of this third part will be scalar potential. We need to get used to the techniques here, calculational techniques. Okay, so the name is the scalar potential or scalar potential functions, lots of names, of vector fields, of a vector field. Okay, so what is this guy? So of course you do have a definition in your study guide, you have a definition in your lectures, and so on and so on. But my task is to teach you techniques, how to deal with it. And that is why I'm going to give you to start with definition again, but I'm going to rewrite it in a maybe different form, from a different approach. So let's start with our given vector field as usual. So we are given vector field, let it be 3 components. Just general case, P, Q, R. So you have 3 functions here, P, Q, R. They're all functions of 3 variables, X, Y, Z, if you remember. If you have the collection of 3 functions, they could be the partial derivatives of some scalar function, d phi over dx, d phi over dy, d phi over dz. They could be. It's not necessarily so. If you just consider the random collection of 3 functions, it's not necessarily that this function phi exists at all. But if it exists, it could be so that these guys are just partial derivatives of the same function. So in this case, we should build the phrase like this. If such function, such phi exists, then it is called scalar potential of our vector field. Scalar potential, or just scalar function, potential function of our field F. So this is the definition. So actually, you should imagine that you are given partial derivatives and you are asked to restore the function itself. with these partial derivatives. Maybe you are even familiar with this task. Maybe from your previous course of calculus, maybe you were dealing with this task because you're definitely familiar with the concept of partial derivatives. You had no problem understanding how I perform this differentiation, and that is why maybe it was in your curriculum how to find this function. But of course, it was long ago. Even 1 month is enough to forget all these things. That is why we are going to refresh your memory, and I'm going to go through examples. But you know what doesn't look very inspiring? This phrase, if such function exists. Yeah. What if it doesn't exist? Situation looks a little bit, vague, as to how to approach this task. Okay, so first of all, I need to write to you the outline of algorithm. It won't be very detailed algorithm. It will be just an outline of algorithm as to how to approach this task. So they usually give you a vector field f, and they ask you to find this potential function, this scalar potential function, how to approach this task, which should be the steps, which approach, and so on. Let's write down the outline of the algorithm. So you're given, again, I prefer to write explicitly what we are given. So you're given f with 3 or 2 components, it doesn't matter, and find phi. They ask you to find phi, this scalar function, potential function. What should be your first step? The step first, check that phi exists. First of all, that the solution exists. Maybe no solution to your problem. How to check it? There is a very famous theorem. So phi exists if and only if the curl of your field is equal to 0. And it's such an important fact that I prefer to put it into the frame. So that's how you can check your existence of phi. And you know, of course, that for 2D case, instead of checking this equality, you can use this nice shortcut, which we discussed earlier. But these are details already. I promise not to go into details, and I'm tempted to go to them. And only after that, after step phi, you can start calculate this phi. I can't go into more details because it's very detailed process, very detailed. As I told you before, this is not the true algorithm, it's just the outline of algorithm. I wanted to point it out to you that it consists of 2 steps. The first step is to check the very existence of this function phi, and only after that you should go to the next step. So I think that the best idea to show you how exactly this happened is to go through some concrete example. And as I said before, this is very technical. Nothing fancy, nothing. You don't need to know a lot about concepts, but you just need to be very technical. Okay, so the first example will be 2D case. Let's start with 2D case. And for this purpose, to this end, I chose question 1b. So in this question, you have 2-dimensional vector field 3x squared y minus y squared, y cubed, I'm not sure, x cubed minus 2x. I hope that I copied this assignment correctly. And find phi. They ask you to find phi. So this is our assignment. This is our task. So according to my outline of the algorithm, in the first place, we need to check. Of course, these are 2 our guys, P and Q. We need to check the very existence of our function phi. It means that we need to check if the field is irrotational or not. Irrotational is a good sign. It means that we can find our function phi. And so for 2D case, we have this very, very nice shortcut. dp over dy is equal to dq over dx. Let's check it. It could be done very, very quickly. Okay, so this function p should be differentiated with respect to y. X gets frozen. So the first term will give us 3x squared, and the second term will be minus 2y. Now let's move to the second function, q. Q should be differentiated with respect to x. So the first term will be 3x squared, and in the second term we have a coefficient minus 2y. Look at this. It's true. It's true. It means that our field, our f is irrotational, and the solution exists. So it does make sense to move to the next step, step 2, which is going to be quite new to you. So I'm going to separate it from here. The problem is that my task is sliding out of view. That is why you know what I'm going to do. Let's discuss first. So actually, our task is to imagine. So indeed, this pair of functions, this p and q, they are indeed the partial derivatives of our function phi. So this should be d phi over the y, and this is d phi over dy. So we actually have two partial derivatives, and we are asked to restore the function phi. But the problem is that it's all sliding out of the view. That is why I'm going to rewrite this information here. So d phi over dx is pi, which is 3x squared y minus y squared. And our second derivative, partial derivative, is x cubed minus 2xy. So I'm going to keep this information here on the screen. That is why I have to rewrite it. Okay. And now we need to find phi. As I said before, I suspect that you're already familiar with this task, but as I said, again, it was too long ago. So how to restore our function? Because if you have a derivative to restore ordinary function of one variable, you just need to do inverse operation to integrate this function. But here we have two partial derivatives. So it means that we can start with any of these. Well, I prefer to start with this guy, this piece of information. So you have derivative with respect to x. That means that you need to integrate with respect to the same derivative. So the way to get our function phi is to take this first derivative with respect to x and to integrate it with respect to x again. So idea is pretty straightforward, I hope. Okay, let's substitute our expression here. 3x squared y minus y squared parenthesis dx. As you can see, we need to integrate this time. And again, the same problem. We need to integrate with respect to x, but we have two variables here. What is the approach? The answer is the same approach as for partial derivatives. You need to imagine that the other variable, which is y, in our case, should be frozen. It should be turned into constant. In this case, this 3y, the first term, will be just coefficient, which remains there. And the antiderivative of x squared is x cubed divided by 3. Okay. And the next component is the whole constant. And the antiderivative of constant is constant times x. And plus c, plus the constant of integration. But the bad news about this c is that it's not c, it's not constant. It's actually a function of y. Very annoying. So we almost have a feeling that we are finished with this task. We almost found the phi, but unfortunately this guy popped up. But how did I determine that it's a c of I, not c of x? The indication is this variable. So you just integrate it with respect to x. It means that your constant should be dependent on y, and vice versa. Okay, so it turns out that we found only like the half of the expression, the half of the function phi. Now we are mystified by this term. How to find it? I could have cancelled out. Okay, maybe I'll do it later. Okay. So it means that we need to use the second piece of information. It hasn't been used yet. And this nice idea would be just substitute phi, our expression for phi, to this expression and see what happens. Maybe we will be able to find our c of y after that. So let's do it. But the problem is that I'm running out of paper. Okay. So I'm rewriting the second piece of information here, just for the convenience. So, and now I'm going to substitute expression for phi here. So the first term is yx cubed minus y squared x plus c of y, parentheses are closing, and the right hand side just gets copied. That's it. Okay, and now I need to switch to the new page, to the fresh paper. Sorry, I'm moving things around here. Oh, it looks nice. Okay, so we need to take partial derivatives with respect to y. Quite a, quite a usual task. So x cubed minus 2y times x and plus c prime of y. We can use this shorthand notation because we have only one variable in the function. This is why it's not necessary to write like dc over dy. It looks much nicer. And the second, the right hand side gets unwritten. So we have this equation. And we need to find c from this equation. But it's a very nice equation. Look at this. These two guys gets cancelled out, as well as these two guys. So we are left with just with nothing. C prime of y is equal to 0. Very nice, very nice. And so we have a derivative of our function. How to find the function itself? We need to integrate, but the antiderivative of 0 will be just constant. Let's denote it like c1. C1 is a better idea. And so all we need to do, we need to take this expression for 5 and substitute c1 here, and that's it. Okay, so let me do it. Phi is equal, I'm just rewriting the first two terms, this, and instead of cy, I substituted c1. And you can denote it as c again for gravity. So that's it. We finished with this task. But you know what? I would prefer to do checking if it's impossible. And this is one of these excellent tasks in mathematics. When you have the opportunity to check yourself, I think it's always nice to know that you can check your result, because especially during the test when you are pressed for time, everyone has a tendency to make careless mistakes. By the way, I'm not sure myself now, I was explaining things to you, but I could be absent-minded in some places. Maybe I did make a mistake. Who knows? Let's check me. So how to do the checking? How to do this checking? So I would strongly recommend you to do checking over every time once you find this potential function. The checking based on the very nice idea. So your first derivative should be equal to p, which is given, and the second derivative over dy should be equal to q. We can check these equalities. If they hold, it means that our solution is absolutely true, 100% of true. Okay, so let's just calculate our derivative with respect to y. So, with respect to x, sorry. So y is frozen. Okay, it means that y remains here, and the derivative will be this one. Here we have y squared, and derivative for c1 is just 0. Okay, and now let's have a look at p. What was our p? 3x squared y minus... look at this. They are equal to each other. Very nice. It looks like we are heading in the right direction. Okay, but it's not the end of the story. We need to calculate the second derivative as well. With respect to y, it will be what? It will be x cubed minus 2yx, if I'm not mistaken. Okay, and now I'm copying q here. Yeah, look at this, the same. So we are cool. We haven't made any mistakes. And that is why it's highly recommended to do this checking. So after the test, you will have a very nice feeling that at least this task was solved absolutely correctly. If your checking showed you that you were absolutely right. But of course, I'm exaggerating a little bit, to be honest. You can make a mistake even here, of course, while calculating partial derivatives, of course. There's no 100% guarantee, but nevertheless, checking is better than nothing. And now, the time is coming to an end, but as said before, I'm not going to stop this tutorial. I'm going to continue. So if you have the next session, please feel free to leave this. I won't take any offense, of course, because I know that you're busy, but I'm going to continue. And what I'm going to do now is I have plenty of time now. I don't have any sessions myself. So I'm going to solve you the same example, the same question 1b, but starting with another piece of information. Okay, this time maybe it will happen quicker. So question 1b again, second method. How to say? Second method. Not method, but second order of steps, second method. So we had this piece of information. Let me write it again here. 3x squared y minus y squared d phi over dy is equal to x cubed minus 2xy. So, and what happened just before? I started with this guy. with this piece of information. Let's start with another piece of information. What happens? You should know how to do it. I need to take a new marker, by the way, because this one is running out. Oh my gosh, I don't know how to open it. It's too tight. I have some scissors here, sorry. Maybe it's even for the better to be silent from time to time. Okay, now I have a fresh marker. So let's start with this piece of information. So what do we need to do? To find our function phi, we need to integrate this expression with respect to y, of course. So phi is equal to d phi over dy this time. And of course, integration should happen with respect to y. Okay, so let's substitute our expression for this derivative here. And this time we need to integrate with respect to y, which means that x gets frozen. So x cubed is constant, and that's why antiderivative will be x cubed times y. And in this case, for this term, you have a constant 2x, and antiderivative y will be y squared over 2 and plus constant, which is not quite constant in our case. It will be a function of what? Of x this time, because we integrated by y, so it should be vice versa. Let's simplify it a little bit, because I'm tempted to cancel out these two guys. X cubed y minus x y cubed plus c of x this time. And let's put it into the frame. So this is our phi obtained from the first step. So we used completely this second piece of information. And to get the expression for c of x, this time we need to use the first expression, the first piece of information. Let me rewrite it here, because it's writing out of view again. So the first piece of information looked like this. 3x squared y minus y squared. And of course, we need to substitute our phi, our expression for phi, into this equation. Okay, so I'm substituting just x cubed y minus xy squared plus c of x, parentheses are closing, and the right hand side is just copied. It's just being copied. Okay, now we obviously need to find the partial derivative with respect to x. 3x squared y minus y squared plus c prime of x. And we are copying the right hand side. Always this expression, this equality, this equation always looks very daunting. But if you look closer, you realize that so many things get cancelled out all the time actually. Not all of them, but most of them. So c prime of x is equal to 0. It means that c of x is equal to constant. Let's denote it c2 just for a change. Okay, so we need to take this expression for 5 and just to substitute c2 or just c or whatever. It's the same constant actually. So I've run out of space all of a sudden by the end of the task. Okay, so our answer will be phi is equal to x cubed y minus x y squared plus c2 or just c, it doesn't matter. So as you can see, we got the same expression, the same function, of course. And of course, I'm not going to do the checking once again. What's the point? We already done the checking. I just wanted to demonstrate to you how to perform these tasks. If you start with, this piece of information, maybe with this piece of information, it doesn't matter. You should just know this trick about C. If you integrate it with respect to Y, it means that your constant will depend on X and vice versa. That's it. That's it. Okay, so we are finished with 2D example, 2D case. And now it's time to move to a 3D example, which will be a little bit longer. I want to see where I prepared this example somewhere just to check myself. Yeah. So let's do a 3D case. 3D case. So 3D case. 3D case. So 3D case. I chose example question 1. I can't see what I've written here. My goodness. I don't know. Question 1, I don't know which one. My handwriting is so bad that I can't see anything. Okay, you will find it yourself. It's not a problem. It's not the biggest problem. So you are given a 3D vector field in this example. The first component is 4x, y, z. The second component is 2x squared z plus 3. And the last component is 2x squared y. Let me check. I need to know the number because so that you can check the answer. Yeah, for B. Yeah, of course. My handwriting was so bad that I couldn't make it up myself. D. Okay, let it be D. I don't care. I'm not caring about it too much. I don't even need the answers to this problem because I can do the checking. That's what I like about this task. Okay, so and we asked to find our function phi, our potential function phi as well. We do have a procedure now, our algorithm, but this time it's gonna be a little bit longer. So okay, so these are our guys. This is P, this is Q, this is R. Sorry, how it's B. It doesn't matter, as I said. Okay, let it be B. I don't care about it too much. It doesn't matter because we don't even, as I said before, we don't need these answers given in your tutorial sheet because we ourselves know how to check our result. That is why this is the beauty of this task actually. Okay, so let's rewrite this information just like in the previous case. So we are given maybe these guys are partial derivatives. No, it's too early to rewrite it because we need to perform the first step to check if this function exists at all. We need to find the curl. Curl should be equal to 0. Only in this case, we have the right to continue with our task. So it was too early. Maybe these guys, this collection of functions are not partial derivatives at all. Okay, so let's start calculating curl. So curl of f, it's nabla cross product of f, which is in turn this determinant. Okay, I can do it quite quickly, no problem. I, j, k is the first row. The second row is symbolic nabla operator. And the third row is our p, q, and r. So p is 4xyz, q is 2x squared z plus 3, and the last guy is 2x squared y. Okay, we already done it before. I mean calculation of the curl, so there should be no problem. And this time I'm not going into too many details because I'm sort of lazy writing all the time. So I'm just going to use this thing. So I'm crossing out the first column. So dy, how to say, the derivative of this expression with respect to y will be 2x squared minus derivative of this expression over with respect to z. It will be minus 2x squared. So I'm done with the first term. It's already 0, by the way. Minus j, crossing out the second column. So derivative of this expression with respect to x will be 4xy minus derivative of this with respect to z will be minus 4xy. It's 0 again. Okay, nice. But it's not the end of the story yet. We need to calculate the third derivative. So we are crossing out the third column. So a derivative of x of this expression will be 4xz, and minus the last derivative of this with respect to y will be minus 4xz. We are very lucky. We have all components been 0. It means that yes, our field, it was out of view. So it means that our curl is equal to 0. This is curl is 0 vector. And this in turn means that our field is rotational. So phi exists, in other words. Phi exists. Very good news. So it makes sense to start using our algorithm, our detailed algorithm. Okay, so let's start a new page. And now I know for sure that these guys, PQR, they are partial derivatives. And that is why I'm rewriting this information here. So the first d phi over dx is indeed equal to pi, which is 4xyz. The second derivative will be equal to q, which is 2x squared z plus 3. And the last derivative is equal to r. So this is my 3 pieces of information which I will need to use during this procedure. Okay, so as you concluded from the previous case, you can start with any of them. Let's start with the first one. I don't know. So I'm starting with this piece of information as a first step. Okay, so to find our function phi phi, we need to what? We need to get this partial derivative, d phi over dx, and of course to integrate it with respect to the same variable as x. So the first step completely coincides with the 2D case. Okay, so what is this expression? I didn't need the parentheses. I don't know why I put the parentheses around this expression. Okay, and so all the variables except x gets frozen. That is why for yz should serve as a constant, as a coefficient, and the antiderivative of x will be x squared divided by 2, and our constant this time will be dependent. You know what? As we just integrated by x, it will be dependent on two variables. Looks pretty daunting, but what can you say? Okay, but we need to simplify this. So phi is equal, this should be divided by 2. It will be 2yz times x squared plus this annoying c, which is dependent on two variables this time. But this is not a problem, because we still have two pieces of information which we haven't used before. So what did we do last time in our previous example? We used the remaining piece of information for substitution. We can do the same here. We can do the same. The remaining two equations, we can substitute phi here and here. This will give us a system of equations. But okay, so let's rewrite these two equations here. So d phi over dy is equal to 2x squared z plus 3. And the last piece of information looks like this. So what do we need to do? We need to substitute our partial derivatives here. But I'm running out of space, I'm afraid. It's better to start here. And besides, I feel a little bit lazy to write down too much. Maybe it's better to calculate this derivative immediately. I think that I hope you won't be minding. Okay, so let's look at this expression and take the derivative with respect to y. I think it's very easy. This writing is really annoying. Okay, so only one variable y we have here, and this is constant. 2z x squared is constant. That is why derivative it will just 2z x squared. And as for the second term, we need to use this symbol dc divided by dy, and of course these arguments. And we are copying the right-hand side of this expression. So we are finished with the first substitution. As for the second one, we need to do the same. We need to calculate this partial derivative with respect to z, which is 2yx squared for the first term, and it looks like dc divided by dz. And the right-hand side is here. But it looks daunting as usually, but usually many terms get cancelled out. These two guys cancelled out, and these two guys get cancelled out as well. So actually, the final equation looks very easy. Of yz is equal to 3, and dc over dx, or dz, sorry, of yz is equal to 0. These equations look much better. And you know what? And now you need to realize that you are faced with this 2D task again. 2D task. You have two pieces of information. So our task is to find this function. Actually, this is function actually of two variables, and we do have two partial derivatives of this function. So this is the repetition of our 2D case now. Again, we can start with any piece of this information, integrate it, and then substitute to another one. So this, you're familiar with the rest of the algorithm. But nevertheless, of course, I'm going to finish it. I'm not going to drop it here. Okay, let's start with the first piece of information, probably. So we have two pieces. Let's start with this one. Let's integrate this expression. So we need function c this time, c of yz. We can take its derivative over y and integrate it with respect to y again. The same principle again. Okay, but this time our derivative is so easy. It's just 3 dy. Oh, sorry. I didn't watch the screen at all. I forgot about this. I got carried away. So this is the piece of information. It's still in the screen. Okay. So what I did, once we cleared up, once we simplified this system of equations, we realized that we are dealing with a very familiar task. We need to find this function of two variables, and we do have two partial derivatives. And we realized that, oh, this is 2D case again. So we need to perform the same procedure. Choose one of these pieces of information and start integrating it. Okay, so, and it turned out to be so easy in this case. So the antiderivative will be 3y plus c1 probably of x, by the way. Do you remember this principle? If you integrate it by y, the constant will be dependent on x. Okay, so c is almost here. Let me write it in this way. So c is here. Put it in the frame. And now we realize that we still haven't used the last piece of information, this one. So what we can do, we can substitute our c there. So let me write this piece of information without arguments. And so I'm substituting my c here, which is 3y plus c1 of x is equal to 0. Let's take a partial derivative. Of the first term, it will be 0. And for the second, something is wrong. I made a mistake. No one noticed because everyone got tired. You know what? My variables in this case are not x and y. They are z and y. So I made a mistake here. Let me correct it with green. So it should be z here. That is why I saw inconsistency, and z here as well. Sorry for the mistake. It's actually very good to make mistakes from time to time because sometimes you get too sleepy, and everything goes too smoothly. Okay, so it means that we have prime of z is equal to 0 again. Oh, very nice, very simple. So c1 prime of z is equal to 0. It means that c1 of z itself is equal to, let's denote it c2. So we are almost finished. Now it's time to find all our separate pieces of information. What should we do with this c2? We need to substitute it here, to finish c of yz. So it was 3y. I hope it's still good. Plus c2. So our function c of yz is equal to this equation. And then what next? We need to substitute it on our expression for phi, our final function phi. Let me remind you. We have this expression for phi. It was in the previous page, of course. This is why I need to copy it for you. So we had this expression. And now we need to substitute this expression here. So the first term is the same, of course, plus 3y plus c2, or maybe just c. So we are finished. This is our final function phi. And again, I don't mind spending time. Sorry, I need to put on the charger. We might be interrupted any second. I almost missed it. Okay, so let's do checking. It's always worth doing checking because who knows? Maybe I did make some mistake. Do you remember? But luckily I managed to find it immediately. But who knows? Maybe I've done much more mistakes. So checking is just a must for me at least. So d phi over dx. Sorry. I need to care about this. So okay, d phi over dx. What is this? 2yz is a constant, and derivative is this, and that's it. All the rest are the zeros. D phi over dy will be 2zx squared plus 3, and the last derivative, d phi over dz will be 2yx squared, and that's it, plus zeros. And now let's compare with them p, q, and r. So I'm looking at the assignment. Yeah, that's correct, absolutely. So q looked like this. 2x squared z plus 3. Yeah, exactly. Look at this. We are clever, we are cool. And q looks like this. Absolutely correct. So it means that our solution is absolutely correct. And we don't even need our tutorial sheet answers, to be honest, for this task, for this particular task. We can see ourselves that our checking works. It means that 100%, everything is 100%. So this was quite a long task, as you can see. A 3D case is the longest one, and that is why, of course, you do need to get practice. And that is why, as a homework to wind up with this chapter, I tried to write it down, but now I can't find it. What are these tasks? I think it's question 1 again, because they do ask you to find this scalar potential. And also question 4. Lots of questions here. So you have such an excellent opportunity to get so much practice. Yeah. Look at this. In question 1, you have like 8 questions. Some of them no. In question Y, you have 2D. Question 1 is about 2D. So you can start with question 1. Maybe it's not a good idea to do all the 8 tasks, but maybe it is. It depends on the person. And after that, you can move to question 4, where you have 3D tasks, 4 3D tasks. So I think, not 4. I've done one of them. So you have 3. You have 3 only here, but it's more than enough, I think. And if you feel that it's even this is not enough for you to do these things almost automatically, you can always find more exercises in the study guide, by the way. So this is this looks like the most involved, the longest task, this finding potential function, especially for 3D case. Okay, and now the remaining part, it's going to be very small, very easy part. Part 4 of our tutorial will be about Laplacian operator. I'm not sure about the pronunciation, by the way. So Laplacian, which is denoted as nabla squared phi. You don't need to know the meaning, at least in this tutorial. You need to know how to calculate it. The secret is very easy one. It's just a very small notation, very convenient, but it can be confusing. You can rewrite it as this: d squared phi over dx squared plus d squared phi. You know what these guys are? These guys are second derivatives, second partial derivatives. That's it. And I forgot to mention that phi is scalar function. Let's write it down. Where phi, depending on 3 variables, is a scalar function, scalar field. Let's use this word, scalar field. That's it. So all you need to do, you need to find these second partial derivatives, add them together, and that's it. It will be a Laplacian. Nothing easier than this. But it's quite a nice news, quite a nice idea to have a very easy task at the end of tutorial when everyone is already tired. So okay, let's go over through question 5a. Question 5a. So you have here you have scalar function, which looks like 3x squared y minus 3xy squared and plus 2z squared. And you ask to calculate this Laplacian operator. So there's nothing easier than this. How do you calculate second derivatives? You should find the first derivative first, and it's like pill on word, and then you can do the rest. Okay, so this is our function. Let's start with the first derivative, d phi over dx. As usual, we mentioned that y and z are constant, are frozen. So this will be 3y and 2x. From the first term, from the second, we will get 3y squared and nothing from here. And the second derivative will be to differentiate the result with respect to the same variable x. Let's try it again. It will be 6y minus nothing, minus 0. So that's it. So this is our first term in the Laplacian. Okay, d phi over dy. Okay, this time only y is our variable. The rest of the guys are constants. So the first term will be 3x squared minus 6xy plus nothing. And the second derivative with respect to the same notation is wrong. It should be here. Okay, with respect to y again. So the first derivative will give us 0 minus 6x. So it will be minus 6x. Good. And the last partial derivative, d phi over dz. So the first term is constant now. That is why 0 minus the second term is constant is again, and the third will give us 4z. And so the second derivative with respect to z will give us just 4. So we are ready to write down this Laplacian. So nabla squared of 5 will be 6y. So this guy, we're interested in these 3 guys. 6y minus 6x plus 4, and that's it. That's it. So as you can see, there's nothing easier than to calculate Laplacian. Nothing fancy. Our previous topics were much harder, much more interesting. So that's it. That's it. So it was plus 30 minutes only this time, not so much compared to the last tutorial. But the next topic, the next tutorial, tutorial 8, will be quite hard as well. So I suspect that it will be longer as usual again. Okay. So if you don't have any questions, we can wind up. Do you have any questions? Oh, okay, that's good. That's good. You're welcome. You're welcome. Okay, so see you next time. By the way, our next time will be on tutorial 8, week 8, which is on campus. But nevertheless, even though I'm going to give you tutorials in person in this lecture theater, but as usual, I'm going to record this tutorial as well because it's quite hard and 50 minutes is not enough. It's definitely not enough to cover all the material. And material is very serious, as you can see, compared to the first module of this class, of this course, of course. So, okay. So I'm